All right, good morning. Um, let's go back and take a quick review of what we were looking at. We were looking at radius of atoms previously. And ions. And I had shown you a nice chart, which I don't know where it is any longer, but it's on the notes. It's showing that as you move for atoms, going from left to right, they get smaller. And going top down, they get larger. This is the periodic table. This is just the general trend. That's the S block, the D block, the P block, and that's referred to that because of the number of electrons in the suborbitals you can fill. And for ions, as you go from a, let's say, lithium to lithium plus, it's lost one electron. It goes smaller. And that is because of the increased Z effective, the overall charge on the remaining electrons. The overall positive charge is more positives than negatives. It can pull it in tighter. And let's say we're going from something such as fluorine. We're adding an electron to it, and we're going to form an F minus. It's going to get larger as this goes this way. You're adding an extra electron, you have more negatives than positives. The Z effective is lowered, the overall effect of the positive charge of the nucleus is lowered, and therefore it can't hold them as tight, making it larger. That's the overall trend. Now, I want to move into an area called ionization energy. And ionization energy, well, what is that? Well, it is the energy required to remove an electron from a gaseous, so gas state, not liquid, not solid state, from a gaseous atom or ion. So it's how much energy you need to do. So think about it. Think of the energy compared to stealing candy from a baby. It doesn't take much versus stealing candy from one of your friends. It takes quite a bit more energy to steal it from them. The removal of the first electron, the energy, sorry, the energy needed to remove the first electron. Oh, if you were having trouble with the atoms and ions, this is page, let's say, page 299 to 302, and that's section 6.2 in your text. I don't know if you can see that, hopefully you can. That was the radius of atoms and ions, and now we're taking the ionization energy. The energy needed to remove the first electron from a neutral atom. is called the, wait for it, the energy needed to remove the first electron. So we're ionizing it, we're turning it from a neutral charge to a positive charge. It is called the first ionization energy. Whoa. And that can sometimes be represented with a capital IE with a subscript 1, the first ionization energy. Subsequent ionization energies, as you remove more electrons, changes. So, what's this energy tell us? Well, it gives us an idea how hard it is to remove. So it gives us an idea how much energy is required to remove. The higher the energy, the more challenging it is to remove. The higher the ionization energy, the more difficult. The electron is to remove. There's a nice figure. That's a C. On page 303, I think it's called a figure. Let me check. Yep, figure. I'm just going to abbreviate FIG. Figure 6.2.4. It goes through and it gives quite a nice chart, I have to say, of these ionization energies. So this can be written as a type of equation. You could write it out as your atom plus the energy required, the ionization energy, will give you gaseous state, plus the electron. There are exceptions to this rule. And one of these exceptions would be oxygen versus nitrogen. You know, if we take a look back here, and it talks about it in here. If we look at here, where's oxygen? Well, as you're going across, well, lithium's got a low ionization energy, we see. Beryllium's got higher than boron. It's easy to remove, and then harder to remove, easy, harder. Now, and that has to do with the electronic configurations and what subshells these are in. All right. So let's just talk a quick second about trends. Trends for the first ionization energy. Okay, this is there are exceptions, and I'm not going to get fully into it. The first trend is Moving left to right on the table, the first ionization energy tends to increase. So think of it as, let's compare lithium to sodium, or sorry, to fluorine. All right, lithium, let's look at the electronic configuration, 1s2, 2s1. Compared to fluorine, 1s2, 2s2, 2p5. So, let's look at this. What do atoms want? They want to get a full valence orbital. They want to be isoelectronic, the same electronically as a noble gas. So, lithium is one electron away from the closest noble gas is helium, where it's 1s2. So this electron to lithium can be perceived as a burden. It would be easily removed. And if we were to look at the values, oh shoot, let me pause this and go look them up quickly. Found what I'm looking for. I like the table in the chart. It doesn't give exact values. Sometimes it's nice to work with exact values. So let's take a look at the ionization energy. The first ionization energy of lithium is 520 kilojoules per mole. Okay, we have no reference. Is that good? Is that bad? Let's take a look. All right, fluorine. Next atom over. 1,681. That's a threefold increase. It's 3 times harder to remove an electron from that, and that is because fluorine has nearly achieved that overall happy state of having a full valence. Where lithium, it could easily say like, hey, I could be persuaded pretty easily, where fluorine's going to be very difficult to remove that. Let's take a look at the noble gas there. Let's take a look at neon. Well, neon has a 1s2, 2s2, 2p6 valence. It has a full octet. How much energy does it take to remove an electron? Do you think it's going to be larger or smaller than this? You're right, it is larger. 2081. Okay. (2,081 kilojoules per mole to remove an electron. So as you see, as we go across, it tends to increase. The more electrons you have, the closer it gets to an octet, the easier it is. So as we go down the periodic table, this is going to be continued on the other side. I've got too many books in my way now. Making a mess for myself. I'm just going to keep babbling. I could have paused it and stopped it, but who doesn't want a Gaffney monologue? 2. This is CHEM11. This is still the 21st of May. I haven't pulled a fast one and changed it on you. All right, trends continued. Okay. So ionization energies moving down, columns. So when I talk about moving across, I'm moving left to right in the same row. Moving down a column, tends to. So think of it, you're getting a larger and larger and larger atom. It's going to slightly decrease. You're going to have slightly lower ionization energies. Okay, let's take a quick look at an exception to help explain why. and I haven't fully gone into some of this yet, so let's go back and look at, so we see it's going up, going up, going up. There's a few exceptions, and what are they? So let's look at nitrogen and oxygen. All right, let's take a quick look at the exception. So if we were to look at nitrogen compared to oxygen, and we are to look at the electronic configuration, we have this. And if you briefly remember from my electronic configuration notes, these are broken up into these groups. So you have a 1s with 2 electrons. You have a 2s with 2 electrons. Now p, the 2p orbital can have 1, 2, 3 areas. And you have 1, 2, 3. Okay, let's compare that to oxygen. So oxygen, there's a 1s, a 2s. S has 1 suborbital, and 2 p's, and all 2 p's have 3 orbitals, 3 suborbitals. There's 4 electrons. 1, 2, 3, 4. And this gets kind of into some other stuff I haven't fully described, but get the general idea. Okay. These are all equal. They're all happy. They're like, woohoo, we're all single. We don't have a pair yet. Whereas these, the p are electrons, and oxygen, 2 are unpaired, and 1 is paired. And oxygen would be like, whoa, I don't know if I like that. I might be able to get rid of this one easier. And nitrogen's kind of like, hey, I don't want to add any. I kind of got a nice little groove going on here. So what we end up with is an ionization energy of 1,402 kilojoules per mole for nitrogen, and an ionization energy of for oxygen of 1,314. Okay, so it's harder to remove an electron when it's got these all unpaired. So whenever you find one of your orbitals are half filled, in this sense they're all unpaired, it's going to be slightly higher. If you go check that table, figure 6.2.4, that graph, you'll follow that along and see that the ones that are usually the halfway point and then the next one over. So it could be P3 and P4, D5 and D6, F7, F8. That's if you get into the lanthanides, actinides. All right, take a break for a sec. Okay, we're going to continue with ionization energies, and I want us to take the idea of I don't know what I'm trying to spell, the removal of subsequent electrons after the first tends to require increasing energies. what's that mean? Let's take a look at an example of beryllium. Okay, so we have beryllium 0, beryllium 1 plus, beryllium 2 plus. So let's look at the electronic configuration. 1s2, 2s2. We remove an electron, we go from 1s2 to 2s1. And you can think as you go down here, the Z effective increases, making it harder and harder. You have more positives holding on to those negatives. And a beryllium 2 plus has an electronic configuration of 1s2, which is isoelectronic, with helium. Okay. And let's look at the ionization energy. And they're going to be in kilojoules per mole. The first ionization, remember that first, it's like, hey, 900. Then you try to get beryllium's second electron off, but they're like, you know what? I don't know if that was a good deal. I'm going to make you work for it. I've got more reason to hold on to this next one. You've taken one away from your iridium. I've got more positives. It's going to take 1,756. So this is the energy required to go from 1s2, 2s2 to 1s2, 2s1, 900 to go from here to here. 1,756 is what it's going to take to go to here. And then beryllium is at an isoelectronic, at this point, Be2 plus is isoelectronic with noble gas helium. Pretty impressive. Be like, woohoo, I have achieved what I wanted to. So what does that mean? How hard do you think it's going to be to take an electron off of that? Well, it's going to take, to remove that noble gas configuration, 14,860 kilojoules per mole of beryllium 2 plus to remove an electron to make it beryllium 3 plus. It is not going to go easily. It's going to have very high values. Okay, I'm going to take a break for a second. I'm going to come back with the definition of isoelectronic. Isoelectronic. Isoelectronic is having the same number isoelectronic having the same number of electrons or the same electronic structure. So, for example, beryllium 2 plus has a 1s2 configuration. That's equivalent to helium 0 with an electron configuration of 1s2. You could say that beryllium 1 plus In this sense, I just purely mean an equal number of electrons, same electronic structure. 1s2, 2s1, it's going to be isoelectronic with lithium. 0, 1s2, 2s1. So you'll be able to have isoelectronic features wherever you're in the periodic table. The definition in the text you have right now, your workbook, I don't like it. Use this definition, please. Okay. Last little bit of notes for today. I'm trying not to go too quickly. I want to make sure you keep up with it if you're watching at home, which I hope you're watching at home. If you are watching at home, send me a message telling me your favorite type of tree. So your favorite type of tree. Little check to see who's listening. Okay, still the 21st. Okay. Now, don't get down on this word. It's actually not the bad thing, but it does play a role and helps you give a really good idea of its trends. Electronegativity. Electronegativity. And what does that word even mean? It is the tendency to attract electrons of the atom, to attract. I'm just going to say, to attract electrons. And it's on a scale of 4. I don't know if it's a linear scale per se, but they're just given the highest value is 4, lowest value is 0.7. So you can check this out on figure 6.2.6 on page 306. I'm going to turn there now. Okay, so that's a good table. It summarizes it. I'm going to quickly summarize myself. Here's our S block. Here's our D block. I'm not going to worry about the lanthanides and actinides. Here's our P block. Okay, as you go from right to left across the table, electronegativity increases. As you go from bottom to top, electronegativity increases. So, I'm just going to mark a few spots on here. Cesium has the lowest electronegativity. At 0.7. Fluorine has highest. At 4.0. Well, ionization energy is the ability to remove an electron. Electronegativity is the ability to attract an electron. Well, that makes sense. Cesium has a really low ionization energy. It can give it up really easily. Fluorine has a pretty high ionization energy relative to all the other halogens. That makes sense. It's going to more easily. So the higher the number, the more easily it steals. The higher the electronegativity value, the more easily the atom can acquire electrons. And so cesium, I left this gap here for a reason, it's large. It's a large atom. And it's, what row is it? 1, 2, 3, 4, 5, 6. It's 6s1. Electron is easily removed. Whereas fluorine is a small atom. It wants its octet. In a smaller atom, the electrons are closer. Are closer to the nucleus. You can also check out page 307. On page 307, figure 6.2.7. And you can see the trends of the electronegativity values are almost the same as the trends for ionization energies. The higher the ionization energy, the more likely it's going to want to become positive and gain an electron. The lower the ionization energy, the more easily it becomes negative. Okay, that's going to be all for today. I will get these posted with some homework actually later on. I just want you guys to work on it. Have some base skills moving to Chem 12. Otherwise, we're all going to be in trouble. Your teachers next year are going to be like, why didn't you learn anything? Like, after you didn't teach us. Okay, well, have a great day. I'll talk to you later. Okay, quick addendum. I want you to work on homework tonight. Page 309 and page 310, numbers 5, 6, 7, 8, 9, 10, 11, 12. So 5 through 12. And I'm going to quickly give two definitions, a cation and an anion. So what's a cation? A cation is a positive ion. Lithium plus. Oops. Cesium plus. Magnesium 2 plus. An anion is nitrogen 3 minus. O2 minus. F minus, a negative ion. So homework. I will write that in a homework assignment. I want you to work on it in your book or on a separate slice of paper. Take a photo, turn it in on Google Classroom. Thank you.